All right, so the last speaker of this day is Matthias Kaminski from the University of Alabama, and he's going to talk about chiral transport in strong magnetic fields.
First of all, thank you all for not leaving me alone after 9 hours of conference. I'm very happy that I don't talk to an empty room. I try to pay it back by making this as interesting and entertaining as possible by telling you about the wonderful world of chiral transport in strong magnetic fields, as this sketch here, this very theoretical sketch of a thermal plasma is alluding to. And then we have holography on one hand side, and then on hydrodynamics on the other. And I also like to bring heavy ion collisions back. So this is a picture looking into the start detector along the beamline and the particle tracks there. And I'd like to motivate what we're doing with that as a focus. So I should tell you why you should listen to me. That's the first question I always ask myself when there's a speaker standing in front of me. So why should you be interested in chiral transport in strong magnetic fields, in thermal plasmas in particular? Well, that's because there's really odd transport happening there. So when I Google odd transport, this is what comes up. And there are various, well, this is the first picture Google image search spits out. There are actually various versions of odd transport happening in chiral plasmas, chiral thermal plasmas in the magnetic field. So one type we looked at already earlier, it happens when you align your magnetic field along the z direction, let's say, to be specific. Then you have a current in the energy momentum tensor, heat current, in equilibrium. So this current is proportional to C, which is the anomaly coefficient of your chiral anomaly. And there's a chemical potential squared, and there's a magnetic field. So you have a heat current that is constantly there in equilibrium. And it's of order, same order as energy, density, pressure, all thermodynamic quantities, you name them. So this is I found quite astonishing. You can think of this as what a cousin of Karl's chiral effects. The only thing you do here is you consider the strong magnetic fields. In most of what Karl talked about, Karl Landsteiner that is, he considered order derivative magnetic fields. So that's odd, as promised. Let me point out a few more odd effects. And I already started giving you a little coordinate system here. So I will, if you have a magnetic field, a strong magnetic field, then you can classify transport along the magnetic field and distinguish it from transport perpendicular to the magnetic field. So for example, let's look at this correlation function, JZ. It's a current correlator along the Z direction, which is the parallel to the magnetic field direction. At non-zero frequency, finally the zero frequency limit, this is related to what we call the parallel conductivity. This is our beloved old conductivity. However, if I take the perpendicular one, JX, so this is perpendicular to the magnetic field, then suddenly, essentially the same quantity, but with JX, gives me a resistivity. But that's odd, as promised. There's another, or some more oddity in this transport. Namely, if I take a JX, off-diagonal correlator, you see that there is a constant term, charge density n over the magnetic field, and then a subleading term which goes like omega squared, which contains this Hall-type resistivity. So this is like a Hall-type resistivity. And there's a JX, correlator. Now I choose to set the frequency to 0 and the momentum limit, take the momentum limit afterwards. And that's related to an anomaly-type transport. This is actually well, essentially the chiral magnetic effect. So there's a psi b here, which is, again, the chiral anomaly coefficient times the chemical potential. Reason to this naming here. So why is there this odd transport, and how can we understand this and classify things? So my motivation is, first of all, to review hydrodynamics and holography, a little bit tribute to Polycastro-Son, Starnitz, and Koftun, who developed this. Then to develop this, for the lack of a better name, I have called it chiral magnetic hydrodynamics. It really is just hydrodynamics done systematically. And then consider a holographic setup where you can actually test if these field theory or effective field theory predictions that you have made are actually correct for this setup that you cook up. And then I'll show you some results and we'll discuss them. Okay, so let's start with a review of this famous result. Eta over S is 1 over 4 pi. The shear viscosity is over entropy density ratio is very low, as even also believed to be seen in the RIC measurements in 2004 after the prediction. Let me recall what shear viscosity really means. It's a momentum transport transverse to the direction of the flow. So we have a fluid velocity flowing this way, and then you have your sheets of fluid, and one fluid sheet pulls on the neighboring fluid sheet, and that way there's momentum transported in the x direction while your fluid flows into the y direction. So transverse momentum transport, that's what shear viscosity measures by Txy energy momentum correlator with itself. And this can be seen from a constitutive relation, which for Txy, which you would write down. It's proportional to your shear viscosity times some tensor structure sigma xy. And if you write this out, then you get the derivative in x direction of uy. That's reminiscent of exactly this, because this is exactly the physics that's behind this expression here. Okay, so after recalling that constitutive equations give rise to Kubo formula, and that has to do with transport coefficients, we can now just put this into up here so that we don't forget these things, and then look at the holographic calculation and calculate this two-point function here holographically. So the holographic model I've chosen here is just the model from Polycastro-Son Starnitz, R minus 2 lambda, Einstein-Hilbert action, and then here's the given Hawking boundary term. And then we have a metric, which is just a black brane metric with a blackening factor 1 minus u squared in u coordinates. From that, you can calculate the entropy density. From a fluctuation calculation in this background, metric fluctuations, you can calculate the metric fluctuation in the xy direction, and that gives you this correlation function using the Son-Starnitz recipe. So I'm not going to review all of this in detail, just a refresher for those people who have seen this before, and for the others, I will just skip through this so that you have at least the facts. So now we can take eta over s, and then you get the famous result, 1 over 4 pi. Good. Now, let me motivate why I would want to use this type of framework, holography on one hand side and hydrodynamics on the other hand side, in this particular setting where you have a strong magnetic field around. My motivation comes from heavy ion collisions, from experiments. So I'd like to derive a general systematic form of chiral magnetic hydrodynamics because you have in heavy ion collisions effects. I know that you cannot see this very well. The point is really just there's data on this plot. That's really the point of this plot. What this plot contains is data from the beam energy scan that's taken by the RIC, by the STAR collaboration at the relativistic heavy ion collider in Brookhaven. And what these people try to find is, with these measurements, is this chiral magnetic effect. So this chiral magnetic effect is essentially charge separation in a particular direction due to the magnetic field in the heavy ion collisions. And that's kind of a novelty to heavy ion collisions. For the longest time, people were arguing that due to the fact that there are charged particles, the heavy ions that pass by each other very closely, there is a magnetic field generated, but it is also decaying very quickly. This idea is being contested by these types of experiments and by the data that people take. One very recent suggestion and run is this so-called Isobaric Collisions run, where you have two ion species, zirconium and rubidium, which are different in their charges but identical in their masses. And what happens there is the idea is in the collision of the higher, the particles with the ions with the higher charge should be more susceptible, should react stronger to this chiral magnetic effect. So it should show a stronger chiral magnetic effect if the signatures produced in these collisions are really due to this chiral magnetic effect. So long story short, there are a lot of endeavors on the way at RIG and also at LHC at the Atlas collaboration to conduct these measurements of this chiral magnetic hydrodynamics effects, essentially. And this, of course, also has a motivation in condensed matter physics, where I understand there's also strong magnetic fields and variable magnetic fields involved in the experiments, probably easier controlled, maybe easier under control than in heavy ion collisions. This will also be interesting for plasma physics as far as I can tell. Also, let me just mention this quickly. The vorticity also leads to a chiral charge separation. This is the chiral vortical effect. And this has become very interesting. And again, I know that you cannot read the data. The point is there is data, and it can be found here. What this shows is essentially the polarization, event by event averages of the polarization of the lambda hyperon, that's a particular particle, and there's a preference in the polarization, or there seems to be a preference in the polarization, which people do not quite understand, but try to attribute to certain vortical effects and polarization effects, which again had not been considered thoroughly before, or had been considered to be negligible before. All right, so the point of this whole slide is there's experimental data on the way right now being taken as we speak that motivates looking at these effects of strong external fields. And I'll focus on the strong external magnetic field. And here's my quick slide showing how to derive this type of, well, it's not a type of, how Landau and Lifshitz basically also went about constructing hydrodynamics. So let's start with a quantum field theory with a chiral anomaly in a charged thermal plasma state subjected to a strong external magnetic field. So I'll say right away that what I'm interested in is magnetic fields of order 1, so not of order derivative. I'm interested in magnetic fields which are still much smaller than the temperature squared. And I'm interested in the hydrodynamic regime where the derivatives, frequency and momenta in Fourier space are much smaller than the temperature. Then we can write down, or some people were able to write down equilibrium generating functionals, also including the anomalous contributions. From that, you can directly derive by variation equilibrium constitutive equations. And here, obviously, I'm leaving out a lot of references. It's just that I apologize. I was out of room here, so bear with me. Oh, sorry. So what I wanted to show you only is this comes from this Koftun and Hernandez paper, which will be cited in a second. So this is the generating functional that is alluded to here. This is a type of generating functional for equilibrium effects. So what you see here is essentially a free energy. It's the type of pressure function, which is a function of only scalars, temperature, chemical potential, and magnetic field squared. All of these are order 1 quantities. And you can have these contributions which come from certain tensor structures. This Sn can, for example, be the magnetic field dotted into the vorticity. That's one example of this. My point here is that these coefficients here are susceptibilities. We can think of these as susceptibilities, and the point of this whole slide is, or of this whole formula, is that our transport coefficients can depend on temperature, chemical potential, and magnetic field squared. That latter thing is the new thing. So my transport coefficients can heavily depend on the magnetic field. And they do, as we will see in a second. So I shifted this over here, and then now just look at also adding time-dependent hydrodynamics. So far, notice that this was just equilibrium. So I'm going to now add the non-equilibrium contributions, very much in the same sense as Mukund Rangamani has done it, and many other people have done it. Most recently, I suppose, Pavel Koftun and Juan Hernandez in this paper, add the non-equilibrium contributions, such as conductivities, shear viscosities, and so on. And from that, you get the full one-point functions or constitutive relations for your hydrodynamics, from which you then can derive Kubo formula, just like I had illustrated on the previous slides. So Kubo formula that relate your transport coefficients on one hand side to two-point functions on the other hand side. And the objective for us would, of course, be to calculate explicitly in holographic model the two-point functions, and from that, through this Kubo formula here, calculate the transport coefficients. And why would we do that? Well, or how would we know that we do this correctly? Well, if we do this holographically, then we can check our calculation, our holographic results, by these relations that both the two-point functions have to satisfy, but also the relations that our transport coefficients have to satisfy. So you will see that it is not going to be easy to satisfy, for example, this relation. These are just, as I mentioned, there are several transport coefficients in here because now we have a magnetic field, which just makes our system anisotropic. So we happen to have, I believe, 4 bulk viscosities, three of which are related through this, this relation here, through this constraint, which comes from an Onsager relation. So Onsager relations are essentially alluded to here. It's basically the behavior of a two-point function under time reversal. And so I unfortunately don't have time to go into detail of this, but these types of relations, as much as the entropy current relations, tells us how accurate our both hydrodynamic assessment and holographic assessment was. So let's look at this Kubo formula in slightly more detail. So on the introductory slide, or on the teaser slide, I had this correlator that was along the magnetic field, and it is associated with, just as we would think, just the conductivity along the magnetic field. And that's understandable. So here's a picture of this situation. We have a current that is aligned with the z direction with the magnetic field. Your charge carriers don't really feel any effect of the magnetic field. So your two-point function divided by the frequency is related to just this parallel conductivity. So this conductivity, recall, can still depend on temperature, chemical potential, and magnetic field. And it turns out that it actually also does. The Kubo formula for this other, like this perpendicular case, where the current is along the x direction, perpendicular to the magnetic field, was more interesting because suddenly we have a resistivity showing up. And this is illustrated here, or we can see this in some more detail in this Kubo formula. So there's a frequency squared here. This is our perpendicular resistivity. This W is just the enthalpy, so it's essentially epsilon plus P, give or take. And then we have a contribution here from what is called the magneto-vortical susceptibility. The magneto-vortical susceptibility is what I mentioned earlier. It's this susceptibility that's proportional to the B dotted into the omega. So essentially you can think of this effect here, or of this magneto-vortical susceptibility, as measuring the current that is created if you spin a thermal plasma in a strong magnetic field. So there's a current generated. A current is generated if you spin a thermal plasma in a magnetic field. Okay, so that's what this idea is. And there can be also some effects of spontaneous magnetovorticity, which is interesting, just like spontaneous magnetization. So these are interesting effects that can show up, and which are captured by this description. So the whole point here was just to mention that we also know the Kubo formula for this magnetovortical susceptibility, and so this gives us the possibility to calculate this derivative with respect to the chemical potential, and then plug in the numbers, and we can calculate this perpendicular conductivity, or sorry, resistivity. Good. I'm running out of time, so I'm just going to go quickly, very quickly through this. This is basically the Kubo formula from the introductory slide. Here we have this Hall type conductivity, which has the twiddle. It is parity odd as a transport coefficient. That's why this is essentially, Hall type resistivity. So it measures the resistivity if you have a current in the x direction and you have it correlated with a current in the y direction, and your magnetic field is along the B field, and the z direction, the third direction. This is your resistivity in that plane, and then you have a anomalous response, which is in the same currents x and y, but you give it a momentum. And so here are the exact formula, Kubo formula, that you get from this hydrodynamic treatment. And so all of this is very, very wild, and it can be even more wild, and I'll flash this only at you. So there's this shear viscosity, which is perpendicular shear viscosity, which is our standard shear viscosity, x and y plane, and then if your magnetic field is perpendicular to that x and y plane, then your shear viscosity Kubo formula is not at all affected, so it's just like this. But then if your shear viscosity is parallel, so that's what we call by eta parallel here, this is this situation, your fluid velocity goes along the direction of the magnetic field, then in this case, there are actually extra terms, one due to this Hall resistivity that we saw on the previous slide, and one due to this perpendicular resistivity. So the point is, this is a horrible mess. But you can also say this is a very intriguing puzzle game. So if all these things in the end consistently fit together, we probably did something right. Or we did something very stupidly and it's just trivially right. But I don't think the latter is true. So because there's constraints that are coming from field theory, there's constraints that come from thermodynamics, and also you can check your holographic reasoning against your field theory reasoning. René is getting up, which means I'm running out of time. It's 1800. So let me just flash the model at you. This is the Einstein-Maxwell-Chern-Simons action that we used. Nothing really to report there. Magnetic black brains, they are charged due to Doka and Krauss. They found the solutions first. Here is basically the formula. You can see all that in the upcoming paper. The point is you have a charge, you have a magnetic field, and you have a chiral anomaly in this model. When you do the calculations, you can do them you face a problem that fluctuations are coupled, fluctuation equations are coupled. So you have two ways of doing that. Doing it like we decided with Karl or found with Karl in a certain numerical way, using this matrix method, and the shooting technique is one way. You will need pure gauge solutions when you do that, and it's a little bit difficult to find them sometimes. There's a nice way that actually was Martin Ammon's idea, and sorry Martin, I have no way of explaining this, or I have no time to explain this further. There's several advantages. You get some analytic results. You don't need pure gauge solutions. Please come to talk to us if you want to know anything more about this. Quick review of the results. So indeed, this is the M5, this is the magnetovortical susceptibility. You know, when you put a magnetic field and you spin your thermal system, your thermal plasma in that, and you observe a current, this is this response coefficient thermodynamic one on a logarithmic scale over the normalized B over T squared, which we call B twiddle. We find that indeed this depends on the magnetic field, and at large magnetic field dies down. Well, actually grows, sorry, approaches a certain value, as you see, as an asymptotic value, which is negative around here, minus 0.6. There are non-zero values. This is, sorry, like still preliminary results. So what this is supposed to show you for different chemical potentials, when you plot against the magnetic field, then your rho perpendicular and your rho tilde perpendicular, so your Hall resistivity and your perpendicular standard resistivity, they are non-zero and they depend on the magnetic field, and I assure you they also depend on the gamma that you choose here. All right, so and there's a bunch of many more transport coefficients which are to be calculated and which we show are non-zero and depend in a similar way on magnetic field, chemical potential, and temperature. All right, so there's no way to show this, so I will just summarize. We find and derive hydrodynamic transport coefficients and Kugel relations for quantum field theory with chiral anomaly in a charged thermoplasma state exposed to a strong magnetic field. We proved the existence of these transport coefficients and the correctness of the Kugel formula with the holographic calculation in Einstein-Maxwell transilence theory. We find that these coefficients are depending on the B, on the anomaly coefficient, and on the chemical potential. We find there are novel transport coefficients, which I didn't really have much time to get into. Then we find that there is order 0 cousins of the chiral magnetic and chiral vortical effect, which I showed in the very beginning only, which already is done here. And then for more motivation for strong magnetic fields, there's actually this paper here which shows a Magneto response which is universal both in lattice QCD and NeCo for superioring Mills. And I'll just leave you with this outlook and I won't say any more. Thank you for your attention.
Questions? Well, if there are no questions, let's thank Matthias again.